Okay, last day we started talking about the different locations on Earth. We talked about latitude and longitude. We talked about the equator, the prime meridian, and how different places on Earth have different biomes, right? Is the temperature in Florida the same as it is in Lethbridge today? Like this morning when I woke up, it was like -5. I highly doubt that it's -5 everywhere else in the world right now, right? We definitely have different biomes. And here's some different reasons why. Latitude, proximity to water, solar variation. We've been learning about the biosphere and the biomes, but our main goal is we need to talk about this word right here. We need to talk about energy transfers. I guess 2 words. Because when it's hot or cold out, when it's -10 or +15, we're noticing those differences due to energy, and different places on Earth have different amounts of energy. As an example, just a really quick thought experiment. Where is there the most energy on Earth? What locations has the most energy? Yeah? The equator. Yeah, the equator generally has the most energy. And the reason we know that, well, a couple different reasons. One, because the equator is actually closest to the sun. Another reason why is though, like we can see all the biodiversity at the equator, right? The equator has so many plants and animals because they get so much sunlight. The least amount of energy is usually found in the tundra and the polar ice caps because but energy doesn't really make its way there very much, and we want to talk about why. On the board over there, like I mentioned a minute ago, here's my goal for today. As you guys, you can see that statement that I put in the box there. I said good science doesn't just try to explain what occurs. We call that correlation. Good science tries to explain how something occurs. It's called causation. Let me give you a non-climate change example right now. Let's say you open up, I don't know, whatever app gives you like basic cool facts or news, and you read this new study that came out. Eating tomatoes prevents cancer. Wow. That's good news, people. We found a way to prevent cancer, eating tomatoes. That's not science, though. That's not good science. I mean, let's say that we've done 100 studies, and we've discovered that if people eat tomatoes, they don't get cancer. That's great news. I guess we've started to stumble into a clue. But why isn't that science? I haven't explained how. All we've figured out is what happens. A leads to B. We call that a correlation in science. Not necessarily a bad thing to have. We like to have correlations. We like to know that studying more leads to better grades, or dropping objects makes them land on the ground. We'd like to know why, though. Well, we know that studying leads to better grades because it leads to better neural pathways in your mind. We know that things hit the ground when you drop them because of gravity. We want an explanation for them. My goal today is to try to give you a good explanation for how heat transfers. It's not just sufficient for us to say heat transfers. Heat moves around, right? Because that doesn't really explain anything. That's just me giving you a blanket statement. In the same way that I'm not going to let it be good enough for us to say carbon dioxide makes the earth hotter. It's true. Don't get me wrong, it's true. But we need to explain why. Otherwise, we're not really doing our jobs as scientists. Okay. So before we move on and talk about the 3 main ways that energy transfers, which are conduction, convection, and radiation, first we better discuss what is heat. Because if we're going to use the vocabulary of heat and temperature and energy when talking about climate change, we better know what heat is. So to begin with, I've got a little YouTube video that I want to show you. There's this guy, he runs a YouTube channel. This is an excellent one for science stuff. Maybe you've seen some of his stuff before. He's going to do a little 5-minute explanation about misconceptions about heat. Let's watch this and then we'll move on. This is a good little video. Except I think we have to, do I still have the old one up there? I do. Here, let's not wait for the ads.
This is chocolate cake. Now those of you who know me know that the only reason I would do this is to...
Okay, from the beginning. Here we go.
Today I'm going to bake this chocolate cake. Now those of you who know me know that the only reason I would do this is to prove a point.
Not to eat cake.
Earlier I was asking people to compare the temperatures of these 2 objects. The science book written by Isaac Asimov and an old metal hard drive. Can you compare their temperatures?
Yeah, that feels colder. Cold. It's nice room temperature.
Can you say colder? Yeah. What makes something hotter or colder? What affects that?
The actual material. I mean, paper is warm and metal is cold.
Both of these objects have been sitting here on the ground for quite a while, so one might expect that they're at the same temperature.
Because this is the metal and that is paper.
But what if
I want to pause for a second here before I let him keep going here. I think he's actually getting at the heart of what I want to describe, is that he's got these people, he's got two objects, right? A piece of metal and a book, and he's asking them which one's hotter or colder. And they're saying, well, the metal one is cold and the other one is hot. But he doesn't just leave it there, right? What is he doing? He's digging deeper, and he's asking them basically, why, right? Like, how does this work? What's causing the metal to be cold versus the paper being hot? Listen to this.
15 degrees?
No, because paper doesn't absorb cold.
Doesn't absorb cold.
No.
One of the reasons why global warming is such a challenging thing to discuss is that there's a lot of misconceptions about heat and energy and temperature, and people don't necessarily know the right words. She just said that paper doesn't absorb cold. Why is that statement so wrong? Yeah. Is there such a thing as cold? Cold doesn't actually exist. Cold is just the absence of heat. Okay, so before we keep going on in the video, let's just do a quick little reminder of what heat is. By the way, I don't think that we should just be picking on this one random stranger, because I bet you if you went around Park Place Mall and asked people this exact same question, I bet you'd find lots of adults that when you try to ask them to explain why something is cold versus hot, as this guy's trying to do here, they would say something, if I can be really blunt, something so silly as paper doesn't absorb cold, right? Like, that is a very, very wrong scientific statement, right? Anyways, let's talk about what heat is. What is heat? Heat is at its particle level, particles, atoms, we've now talked about chemistry, at its like smallest chunks of matter, protons, neutrons, electrons, atoms, they're vibrating. Okay? All particles are vibrating unless we ever get to a temperature called absolute zero. Ever heard of absolute zero? Yeah? Cool. Yeah, in theory, if we could stop the vibration of particles, which we've never been able to, but in theory, if we could stop them entirely, then if particles never vibrated, you'd be at the lowest temperature possible. Because really, temperature is a measure of heat, and heat is basically as particles vibrate. Okay. So what makes something hot? Well, we feel heat because as particle A, you need to kind of watch my hands here, by the way, so I'm going to go to the front of the room. As particle A vibrates, and particle V is really not vibrating, as this one bumps into this one, it kind of transfers a little bit of its vibrationalness, right? If I'm like doing this and I'm bumping into somebody, I jostle the person next to me, and they jostle the person next to them. That's heat. We feel heat as the flow of the jostling, right? As an example, imagine that there was a fire drill. All of us have to get evacuated out into the hallway, and we're like really squished in together, right? Now, normally we're just, standing kind of nicely like this. But what if one person, being a real jerk, at the back starts pushing? That's kind of what heat would be like, where because I get pushed, then I get pushed, and then I knock into the person in front of me, and more jostling occurs. Can I use that word, jostling? That's the transfer of heat. Does that make sense? So is there such a thing as cold? Well, no. Cold is a particle that's really not vibrating that much at all. Hot is a particle that's vibrating way more, and as those particles vibrate and bump into other particles, that transfers what we call heat. But heat really isn't a thing. It's not a tangible object. It's just basically, it's kinetic energy being vibrated. Let's keep watching this video here.
Well, I've left books out, not all day, outdoors, and I can't say that I've noticed the book was cold when I come in here. Yeah.
What if I told you that these two objects are actually the same temperature? What would you say?
Definitely not. Because the temperature right now, this is colder.
So let's say you're taking a cake out of the oven.
Yeah.
Would you be worried about touching the cake?
Yes. Well, not the cake itself, but the actual tin around the cake, because it'll be hot.
Yeah, but how does the temperature of the tin compare to the temperature of the cake?
Well, the cake will be warm, like hot, but not as hot as the tin.
The tin's hot because it's metal. Metal holds the heat longer and holds the cold longer.
Like
You
you
know
have
the
to,
tin would be the same temperature as the cake?
well, you think it's been like 200 degrees Celsius, I would probably be the same, but it somehow, it just doesn't feel like it will burn with metal, whereas my fingers will burn. But I mean, not if I stick my finger in the cake, it wouldn't burn as much.
Alright, it's time to take the cake out and find out if it's the same temperature as.
Okay, before we do this experiment right here, just don't answer this out loud, but just kind of think to yourself, he's baked a cake in the oven, right? He's now going to take the cake out of the oven, and the question he's posing is, which is hotter Or another question is, which has more temperature? The piece of metal that the cake is resting on, like the pan the cake is on, or the actual cake itself? Right? What do you think? Don't need to answer, but think to yourself, what's going to be hotter? Is it going to be the metal? Is it going to be the cake? Or will they have the same temperature when they come out of the oven?
The tin. I have a meat thermometer with which to measure the temperature of the cake. I'm not sure that's the most accurate way of doing it, but, well, it's the only thing I've got. So let's give it a shot. So I tried to measure the temperature of the cake using a meat thermometer, but unfortunately its temperature scale doesn't go high enough to allow me to accurately measure the temperature of the cake. You can actually hear the moment when I realized that my experiment wasn't going to work. Uh-oh. So now I'm back in Vancouver, and I thought I'd bring in the big guns to help me sort out this experiment. Big guns, of course, mean my mom.
So, Derek, I understand you're going to make the vanilla cake mix together and see what happens.
I think he just wanted his mom to make him cake, honestly.
This infrared thermometer, which can measure temperatures up to 300 degrees Celsius, so we should have no problems with that. We just point it at a surface, and it gives us a readout of the temperature of that surface. So this should be perfect for measuring the temperature of the cake and the tin. Do you want to make a prediction about the relative temperatures of the cake and the tin when we bring it out of the oven?
Well, I really suspect that the tin is going to be a lot hotter than the cake. You can read.
Okay, so think to yourself here. I don't want you to put up your hands because I don't want to embarrass anybody if you get it wrong, but I think there's three possibilities. Is the tin going to have a higher temperature than the cake? Is the cake going to have a higher temperature than the tin? Or are they going to be the same as each other? I think those are the only possibilities. Okay. Think about that as he does his experiment.
Handle the tin at all. So I reckon that's what's going to happen.
Okay. Well, I think they're both going to be the same temperature, but I could be wrong. So we're going to have to do the experiment and find out.
All right, let's get mixing.
Okay, so it's been about half an hour, and the cake is cooked, ready to come out.
Yeah, we're all ready to
That
go.
is your expert opinion as the master baker here.
There's something so.
Okay, we're going to take the cake out of the oven, and we're going to check the temperature of the tin and the cake. Let's do it. Ooh, it looks like a good cake.
Yeah, not bad.
Okay, so let's measure the temperature of the cake. We have.
108.9.
And the temperature of the tin.
118.6, but dropping.
Over here.
108.1.
So we have, what would you say about the temperature of the cake and the tin?
Pretty close. Much closer than I expected.
They're quite similar. They're both around 110
Yes.
Celsius. That's my point, is that the tin and the cake are the same temperature. But the tin is going to conduct heat to your hand much faster than the cake. So the tin would burn you, but the cake would not. But the
So we need to pause here because we need to have our vocabulary right. Both the tin and the cake have the same temperature, 110 degrees or whatever it is. Why? Well, they're both been in the same oven. They're both in the same temperature. However, it wouldn't be incorrect for someone to say that the tin is hotter than the cake because heat is more of an abstract concept. Heat is about how one molecule bumps into the next molecule, which bumps into the next molecule and causes everything to vibrate. Certain objects are better at causing those vibrations, metal being one of them. Metal is very good at transferring its energy, so to speak. And so all of those vibrations in the metal, it's very easy for those to get into someone's fingers and you can burn yourself. You know when you use oven mitts to try to grab the cake out of the oven? The cotton or the silicone or the fabric of your oven mitts, it will also conduct heat, but it doesn't transfer quite as easily. Right? There are certain things that are, as particles, very good at vibrating. There are other things that are very good at vibrating, but they're not as good at transferring their vibrations to the next person, the next one in the row. And that's what he's basically discussing here. So would it be fair to say that the tin is hotter than the cake? As long as we're describing heat as the flow of energy from one object to the next, yeah, the tin is able to transfer the heat from one object to the next very easily, as opposed to oven mitts. But are they both the same temperature? Yes. Okay, I'll just let him finish this video and then we'll move on here.
same temperature. What if I were to impress upon you that they are in fact the same temperature? And that in fact that these two are the same temperature? You don't think they're the same temperature?
Really? I just can't believe he's put this into degrees. It just doesn't feel it. I just can't believe it.
In truth, there's no difference in the temperature between these two objects. If they've been in the same surroundings for a long period of time, they come to thermal equilibrium with their surroundings, which means they're both the same temperature. But the metal feels colder because it's able to conduct heat away from my hand faster than the book.
What is cold? Cold is just you losing the energy of vibration to somewhere else. Say you go outside in a minus 15 day and you're not wearing your coat outside, right? And you feel cold. It's not that the outside environment is doing anything to you. It's the fact that the vibrations in your body warmth system are being transferred outside of you to the cold air, right? And so your molecules of your skin are vibrating, and they're causing the really not vibrating air molecules to try to vibrate. And it's basically stealing your emotional energy, your kinetic vibrational energy. Does that make sense? Well, certain things do a better job of stealing your energy. This book right here is more of an insulator. And so although the vibrations happening in this guy's hands right here are quite a bit, the book doesn't really steal quite as many of them because it's just not very effective at that. Whereas this metal right here is the same temperature, but it's much better at taking those vibrations and transferring them from one to the next. Meaning that this guy's hand feels cold because you can feel the vibrations being lost in your fingers to the metal. Just because metal conducts better. So, are temperature and heat the same as each other? No, temperature is a way of us measuring, degrees Celsius, but heat is all about transferring from one thing to the next. And there's really just a relative scale. There's either hot, where you have vibrations, and cold, where you don't. Okay.
So
That's...
an object feels colder, that doesn't mean it actually has a lower temperature.
All right. Anyways, we'll stop there because that's hit the point I want to make here. We've then, ideally, at some point in your... I'll leave the light off here, actually. At some point in your science lives, maybe grade 7 or grade 8, I forget what year you learned about it in, you should have learned about 3 words, conduction, convection, and radiation. I want to do a quick review of these ones again here and talk about what's happening then. Conduction is what I've just been discussing, the idea of different particles bumping into each other here. And particles with more kinetic energy transfer their energy to neighboring particles by vibrating. If I'm vibrating and I run into you, and you vibrate and run into the next person, that's basically the definition of heat transfer. Okay. I like this picture right here. This model right here, I think, is a good way of kind of describing how conduction works. If we can get this molecule right here vibrating, well, it's going to cause the one next to it to vibrate, which will cause the one next to it to vibrate, and so on. And it won't just cause them to vibrate in a row, but it'll cause the one below it and to the side of it to vibrate. That's conduction. Does that sort of make sense there? Okay, there's a second way that particles can move, and it's known as convection. Okay? Convection becomes really important when we eventually want to talk about weather patterns, things like how we have trade winds, how breezes work near the sea and the ocean, how hurricanes and monsoons form. We'll want to talk about that. One of the principles of convection is basically this one right here. I'm just going to highlight it for us. When particles heat up, they tend to expand. I want to talk about why. Say you have this kettle right here. This kettle right here has some particles that hopefully you'll agree they're starting to vibrate right in this area here. So I'm just going to vibrate them around like this. But what happens to particles as they vibrate? Well, as you vibrate more and more, you tend to spread out to more locations, right? If you have more energy, you'll tend to spread out. And so these particles want to spread out a little bit more than normal. Okay. Well, that actually causes them to become less dense. They're still the same number of particles, but they're in a greater area. What that does from a physics point of view is it makes them less dense. And we know that less dense things rise. Does a helium balloon disprove gravity? No. No, it doesn't. It just means that helium is less dense than the air around it. And so although we can't see it, gravity is actually pulling the other air below the helium balloon. And the helium balloon looks like it's rising, but that's only because air molecules are going below it, causing it to rise, because it's less dense than the air itself. We just can't see the air particles that are actually being pulled underneath it. Long story short, this water in this kettle right here is expanding. As it heats up, it becomes less dense and it rises. And if I could kind of use my mouse just to illustrate like the vibrations. So just kind of watch here. Here by the flame, there's a lot of vibrations, right? Vibrating things expand, and so as they expand, they begin to move upwards because they're less dense. But now we're further away from the flame. And so as these particles are bumping into each other, eventually they're going to slow down. Well, if they eventually slow down, we now call them cold. right? They've lost their energy because all of these particles have bumped into each other. They've moved up. They've now lost their energy. They're not really vibrating all that much. Well, now they condense. Now things that are more dense fall until they work their way back around to here when they get near the heat source and they go, oh, now we can vibrate some more. As they vibrate more, they expand. They go up towards the top, but now you're away from the heat source, so you don't vibrate as much, which means you're cold. Colder things are less dense, and so they fall back down again. That's called a convection current. Okay? It's really the main principle behind how our Earth manages to heat itself within the atmosphere. Okay? Actually, I've got a picture for this one as well. There's a classic experiment that sometimes teachers will do. I didn't bother to grab this stuff because I think I can explain it just with a picture. What you do is you take a beaker and you drop in a few potassium permanganate crystals. They're pink. And what you do is you put a little burner near it. And what you can actually see happen is the purple crystals right here will start to rise up and rise up and rise up, and then kind of go over to the side and fall down. And they start to make a circular pattern due to what's called a convection current. Hot things rise. Okay? Here's the last one. I want to talk about radiation. Radiation is the third way that energy gets transferred. But a lot of times, especially in grade 7 or grade 8 science, and even to be honest in grade 10 science, we just tell kids, radiation is what causes things to heat up. Like this is a very typical slide. We would say something like this. Radiation is also the transfer of thermal energy through waves found on the electromagnetic spectrum. When energy is absorbed, this causes an increase in temperature. But to me, that's not good enough. When I just say that energy is absorbed, it causes an increase in temperature, we should really discuss why. Why does radiation work? Why does you sitting near a fire cause you to warm up? It's not just enough to say, stand near a fire, you'll warm up. We should describe, well, what's actually happening here. Where does Earth get all its energy from? Earth gets energy from the sun, right? Here, I'm just going to draw a brief picture here. Here's the Earth. And way far away over here, so I'm drawing it smaller, even though the sun is way bigger, I'm going to draw the sun. And the sun sends its energy to the Earth. However, what is there between the sun and the Earth? Nothing. There is literally nothing here. We call it a vacuum. And this is really important. I think there's not two C's, there's just one C of vacuum. There's nothing here. There's a vacuum between the sun and the Earth. That means that we can't have a particle here bump into this one, bump into this one, bump into that one, bump into that one to get energy to the Earth. And if we don't have particles between us and the Earth, it's not like we can get a circular pattern of energy going like that. And yet, the Earth is not getting colder. It's actually getting warmer. So clearly, there must be a way for the sun to send energy from here to the Earth. But the question is, how? It's not just sufficient for us to say, it happens. You know what I'm saying here? But a lot of times when we teach about radiation, if I can just go back to the slide right here, we stop here. We just say, when energy is absorbed, it increases temperature, and it's due to the electromagnetic spectrum, but I don't think we explain why. Okay? The rest of my lesson here is going to be very technical, but I don't want to just stop. I think that's bad science. If you don't fully understand the next 15 or 20 minutes of my lesson, please don't worry about it. I will keep trying to explain it to you. But to me, this is the most important part, because if we're going to talk about global warming, we have to try to understand the mechanism. Okay? Much of this is actually physics 30. So I'm not going to dumb it down. I'm going to try my best to explain quantum physics to you, even though you're only, finger quotes, only in grade 10. But I believe you can understand this, okay? But if you don't, please don't freak out and be like, I'm totally lost. Let's try to explain how the fire right here sends radiation to your hands. And in a similar way, let's talk about how the sun sends radiation to the Earth. Okay? Here's where we're going to start. We're going to start by talking about infrared radiation. Okay? The guy in the video was using what was known as an infrared gun. He was just shooting the gun towards an object, and it was reading out its temperature. And you could probably ask the same question. Okay, it works, but how? Right? Just like I have written up here. Good science doesn't just try to explain what occurs. It tries to explain how. Let's start with this right here. All objects in the universe, we know that they're vibrating. Right? We just talked about that. If you have any heat to you at all, you're vibrating. This is an infrared picture of a wolf. Okay? You guys ever heard of night vision goggles? Where in theory you're supposed to be able to see at night? Well, that's what this thing more or less is doing. It's giving you a picture at night when you can't see with light. But you can actually see this wolf right here. The eyes and the mouth actually have the highest temperatures, and like the fur over here has the lowest temperatures. Okay, let me try to explain why. All matter is vibrating. We can start with that premise. Well, one of the physics principles that you'll learn about if you ever take Physics 30 is that vibrating particles give off electromagnetic radiation. And so before I keep going with that, we better do a quick recap of what electromagnetic radiation is. Here is the spectrum of what we call electromagnetic radiation. You may have learned this in the past. For example, radio waves are a type of electromagnetic radiation. Visible light is a type of radiation. Gamma rays are a type of radiation. The basic concept is, there's really two things you need to know here. The more that particles vibrate, the faster they vibrate, the different frequency they have. And the different frequency they have tells you what type there is. Radio waves, right here you can see, they don't vibrate very quickly. They have what's known as a low frequency over here because they have low vibrations. I mean, they're still vibrating, but these particles give off smaller wavelengths, so to speak. Whereas gamma rays over here have much higher rates of vibrating. You guys can see how this thing goes up and down a lot quicker here. Faster vibrations, therefore these things have a high frequency. Okay. You and I and that wolf in that picture, we're all vibrating. So what sort of vibrations do we give off? Well, we actually give off vibrations in the infrared spectrum. But our eyes can't see them. Our eyes cannot see infrared rays. But I want to stop talking about the wolf for a second here. We actually can see the effects of something where it's vibrating even faster. Let's go back to that oven that the cake was being baked in. That oven probably has a heating element in it. What's happening to that heating element? Well, the particles are starting to vibrate, and as they vibrate, they give off infrared rays. However, what happens if it gets vibrating fast enough? What color does the heating element glow? Red. Guess what's next on the spectrum right here? Red. You've seen this before. You must have. As you heat up an object, sometimes you can heat it up so much that it glows red, sometimes orange, sometimes yellow. You may even heat an object up enough that you can actually see it glow blue. Okay, we've actually done that in this class before. I burned some methanol on the table right there. Methanol burns blue. That's because the molecules are vibrating so fast that they're not just releasing off invisible infrared rays, they're not even releasing red or yellow or green, but they're releasing blue. You ever heard the phrase white hot before? White hot, ever heard that phrase before? Sometimes you say that it's white hot. Okay, it means it's really hot. Well, white hot is so hot that not only does it not glow the infrared spectrum, which we can't see, it doesn't just give off red, orange, yellow, green, blue, purple. It gives off all the colors of the rainbow. And when all the colors of the rainbow combined, you see that as white. Our sun is vibrating, and we actually see the sun as about a yellow color because of how fast those vibrations are happening. So, long story short, you and I, everything in this room, is giving off infrared rays. Can we see those infrared rays? No, we're not vibrating fast enough to give off a ray that we can see. But you have seen this before. If you were like a blacksmith who's putting a sword into the furnace, and then later you pound it, ooh, just drop that, and then you're pounding it with your hammer on like the big anvil, and it's glowing red, you've heated it up so much that it's not just emitting infrared, it's actually emitting red, and maybe even orange. Okay, let me go back to the wolf then. This wolf right here, and you and I, we can then see with infrared technology where the warmest sections are. Over here, these particles of the wolf's fur don't really vibrate quite as fast because they're not as warm, and so they therefore have a lower temperature. But the mouth and the eyes and the ears, those are the warmer areas on the body, and because they're warmer, they vibrate more, and because they vibrate more, they give off more infrared, so therefore we see that color. So that's first physics principle you need to know. All matter is vibrating. Vibrating matter gives off rays. The rays that are given off are generally in the infrared, so human eyes can't see them. Unless they vibrate just fast enough, you can get into visible light. Yeah? Yes, it does. That's actually my next topic. Thank you. That's actually just perfect here, because that's my next slide. So let's go back to the sun now. The sun vibrates with a few different frequencies that can be released. It doesn't just release one frequency. It releases three main ones. It releases ultraviolet light. I don't like this slide here. It said invisible light. I think we should just call it visible light, though. I mean, we can see it, right? And then infrared. Those are the three main waves that the sun sends towards the Earth. So now we're back to the question, how does this heat the Earth, though, right? We get that clearly somehow energy is coming from the Earth to the sun, or from the sun to the Earth. There is nothing in between here, and yet energy is being absorbed somehow. And that's my next slide. There are three things that can happen to waves. Here's the three things. As radiation comes in, which is basically what the sun is giving us, light is radiation, X-rays are radiation, gamma rays are radiation, radio waves are radiation. As radiation comes, there's three things that can happen. One, it can be reflected. Two, it can be absorbed. Three, it can be transmitted. Those are the three things that happen. Either the wave bounces off, the wave goes through and gets absorbed, and sometimes it kind of comes through the other side. Those are kind of your three most logical things that happen to a wave. Before I talk about how heat occurs due to the absorption of radiation, I want to talk first about how we see things. How do I know you're real? How do I see color, for example? Well, here's how this works here. I'm going to start with red. Let's use this picture actually. Say you have a red apple. The sun is sending all sorts of waves towards the Earth. It's sending infrared. It's sending red, orange, yellow, green, blue, violet, and it's also sending ultraviolet. A whole spectrum of rays are being sent towards us. Many of those rays are absorbed. You can see here that yellow, green, blue, purple, they're all being absorbed by the apple. And we see red because the red waves are the ones that bounce towards our eye. Okay? What you're seeing is the non-absorbed waves, the reflected waves. Okay? When I see Gabby's blue sweater, here's what I know then. All of the other colors of the rainbow were absorbed by her sweater, except for blue. Blue was absorbed and then bounced back towards my eyes, and therefore that's how I see the color of blue. What about white and black? White reflects everything. When you see something as white, you're seeing all of the colors of the rainbows being reflected. When you see black, you're seeing none of the colors of the rainbows being reflected. When you see something that is truly a black color, you're seeing nothing. Can I say that again? When you see something that is truly a black color, you are seeing nothing. You are seeing the absence of rays reflecting back to your eyes. Remember how cold is the absence of heat? When you see this black object right here, it's because there's nothing to see. Is there actually an object there? Yeah, but there's nothing actually reflecting off of it, and your brain is interpreting that nothingness as the color black. One of the reasons that why this occurs then is that as it gets absorbed, it starts to heat up a little bit. Right? If you were to go outside and wear a white shirt versus a black shirt, maybe you know this, but a black shirt usually absorbs more and heats up, whereas a white shirt is more reflective. This is one of the reasons why we know that global warming is a problem not just for carbon dioxide. When we build parking lots and buildings, things that are black in color, like an asphalt parking lot, it absorbs all of those rays from the sun. Does that make sense? Because that's what we know black things do. Black absorbs, white reflects. Colors reflect just one little section of things. Okay, so then the question is, well, what happens when things get absorbed? Here's where kids get a little lost. I'm sorry, this is quantum physics. This is cool, though, so I hope this makes sense here. We have learned in our chemistry unit about something known as Bohr's energy levels. Remember on the periodic table how there's different energy levels available? Hydrogen and helium are level 1, lithium, beryllium is level 2. And know how electrons are supposed to live in those levels? This is maybe not the best picture to use yet. Why don't I use this picture here? Do you see how here's an electron on the first ring, and now here's an electron on the second ring? What is happening when energy is being absorbed is electrons in general bounce up an energy level. That's what happens. So if an electron was on level 1, when light, or a photon is often a word we use there, when some sort of radiation hits that particle, it causes it to bounce up an energy level from level 1 to level 2. And here's another picture that kind of describes that. Here's a photon of, say, light. A good way of describing this is as a wave. When a wave gets absorbed, what is actually happening. I don't just want to explain the what, I want to explain how this occurs. This particle right here absorbs that energy and goes up to the next level. So if I were to draw a picture here, here's a nucleus. Here is energy level 1, here is energy level 2, here is energy level 3. Much of our world is made of carbon and oxygen. So why don't I draw a carbon real quick here. Carbon would have 6 protons, for sure, which means it has 1, 2, 3, 4, 5, 6 electrons. Okay. Well, as light or infrared or some things along those lines gets struck by molecules, in comes a wave. The wave hits the electron, and the electron goes up to the next energy level. Maybe it even goes to this energy level, and it sort of bumps up. That is how the absorption happens. Now, it really depends on what's being absorbed, though. If I can go back to this slide right here, all of these different things here have a different amount of vibrational frequency. And so some of these things cause motion a little bit more. Visible light causes electrons to bump up an energy level. But there's other things that can occur as well. I'm going to use this slide here to talk for a second. Depending on whether you have X-rays, ultraviolet rays, visible light, infrared, or microwaves, different things happen. Okay. I'm going to start with ultraviolet. You guys know about solar panels, right? The idea of how we can use the sun's rays to create electricity. Ultraviolet has enough energy that it can actually cause the electrons not just to bump up an energy level, but we actually call it ionization right here. What happens is a ray comes in, it hits the electron, and the electron doesn't just bump up from level 1 to 2, or from 2 to 3 or 3 to 4. The electron leaves the atom entirely. Electrons moving is electricity. So X-rays, which the sun doesn't really provide us, but ultraviolet rays, which it does, causes not only for an electron to bump up an energy level, but it actually can cause it to leave entirely, which is where solar panels come from. Visible light causes electrons to change energy levels. Okay, let's go back to infrared then. Infrared, which is kind of what we use to describe heat, infrared doesn't have enough energy to cause electrons to move. But what it can do is cause molecules to vibrate. Pause for a second. What is a better definition of molecules vibrating? Heat. So when infrared radiation comes in and hits a molecule, it causes that particle to vibrate. It could cause the electron to move around a little bit. Okay. Here's another one, microwaves. You know the microwave that's sitting over here? You know what a microwave does? It causes molecules to rotate, specifically water molecules. There's water molecules in basically all food particles. By getting those water molecules to start to rotate a little bit, it heats them up, right? Isn't rotating going to be the precursor to vibrating a little bit? So microwaves cause molecules to rotate. Infrared causes molecules to vibrate. Visible light causes electrons to bump up energy levels. And ultraviolet causes electrons to leave entirely. It really depends on the type of radiation that you have. And this is a summary slide then of what I just talked about. Okay. You're gonna have to stay with me right till the bell. I'm sorry, I'm kind of timing this right to the buzzer here. What does microwaves do? Molecules rotate. The wave comes in and causes molecules to start rotating. Infrared causes molecules to vibrate. This is the one we're going to care about when we talk about global warming, by the way, because this is what causes things to heat up. Visible light causes electrons to jump up energy levels, and ultraviolet causes electrons to jump not only energy levels, it causes them to be what we call photo-emitted. The electrons jump up an energy level, and they jump so far, they leave entirely and create electricity. Okay. I have 2 more slides. Please stay with me. I have 3 more slides. Here's an example then of what carbon dioxide does in our atmosphere. Okay. Carbon dioxide then causes this dip right here. Okay. Imagine that this is supposed to be, say, X-rays, and this is supposed to be, no, that's the wrong side. Let's do it this way. Let's make this radio waves, and we'll make this infrared. We'll make this red, orange, yellow, green, blue, indigo, violet. Here's what carbon dioxide does to the spectrum of stuff coming from the sun. Okay. As the sun sends all of its radiation, it should be 100% radiation, but not all of it makes it to the Earth. There's a big dip here. And the reason why there's a dip is that infrared, as infrared comes in, different wavelengths interact differently. the infrared wavelength causes carbon dioxide molecules to either stretch a little bit or to vibrate a little bit. But again, what do we call stretching and vibrations? Heat. Okay? Other wavelengths phase right through them. Carbon dioxide does nothing to green light. Carbon dioxide does nothing to red light. Carbon dioxide does nothing from radio waves. But carbon dioxide is especially sensitive to infrared. And because it's sensitive to infrared, it causes it to vibrate. And therefore, it heats up. Second last slide. Let's say you're standing outside, hot day outside, and you're standing outside here in the sunshine, or you're standing outside over here in the shade. What's the temperature in each of those locations? It's actually the same. Just like the opening video, it's 25 degrees right here, probably 25 degrees right here. But you'd say, Chris, it doesn't feel as hot in the shade as it does outside right here. But that's because we're discussing the wrong thing. The temperature is still 25. It doesn't feel as hot in the shade because over here, infrared lights from the sun is coming, hitting your body, and causing your molecules to vibrate more. When your molecules vibrate more, you get warmer. Does that make sense? Whereas if you're standing in the shade, are those infrared molecules hitting your body? No. But in both cases, it's 25 degrees. You just feel warmer because direct sunlight is causing your molecules to vibrate more. Specifically, infrared does it. White light doesn't do it. X-rays don't do it. Ultraviolet doesn't do it. It has to be infrared. This might lead to the thought of, well, hang on, Chris. If rays of sunlight come and hit me, and I start vibrating more and more and more and more, will it keep heating up and explode? Bad timing. I really want to finish this. Can you guys give me 1 minute, please? If you got to take off, take off. It might lead to the thought then, well, why don't we just keep vibrating more and more and more and more and just heat up till infinity? Well, the reason why is we not everything before. We have what's known as a radiation budget. As energy comes in, it is absorbed. You have 100 coming in, and if you add up all to 100, what happens if you have 100 coming in? You're starting to heat up. That's where we'll end it. Thank you guys for being patient. We'll talk more tomorrow.